Okay, so welcome back. And right now we're going to talk about the relationship between change in free energy and spontaneity. And what I mean by change in free energy is this term right here. Now, that's a much different term from this one. This here is standard free energy, whereas this is free energy. This term here gives us a much better indication of spontaneity. When delta G is negative, the process is going to be spontaneous in the direction indicated. When delta G is positive, the process is going to be spontaneous, but in the opposite direction indicated by the reaction. And when delta G is 0, the process is at equilibrium. So at what temperatures is the following process spontaneous at 1 atmosphere? So this is the process. So in other words, turning from monoclinic sulfur to rhombic sulfur. And so what we're going to have here is we're going to have an inspection of delta G being equal to delta H minus T delta S. Now a couple things to remember is we need to have unit agreement and T in Kelvin. So in other words, T and K is temperature in Kelvin. So with that in mind, we can come here and we can have delta G is going to be equal to negative, and we're going to call this 300 joules per mole minus, and at this point might as well assume 25 degrees Celsius, so that would be 298 Kelvin times 1 joule per Kelvin mole. Alright, and so let's see what delta G is going to equal. And so we have negative 300 minus 298, and then that's times 1, so as long as we're writing in all our units, let's suppose clean this up. So minus 298 times 1, and so we have negative 598 joules. Alright. So, at this point, we've got a negative value, so spontaneous at 298 Kelvin. So let's go the other way. Let's see if it's going to be spontaneous at 0 Kelvin. Alright, so we'll change this to 0 Kelvin. And at that point now we have a 0 multiplier, and so the answer for delta G is still going to be negative 300 joules, which means it's still going to be spontaneous in the direction indicated. So now let's go in the other direction. What if we make it a really big temperature, like 1 million Kelvin? So now we would have negative 300 minus the quantity 1 million times 1, and we get a very negative delta G value in that case. And so what we're finding then is that at all temperatures the process is spontaneous. So pretty much another way that we could have set that up is we could have set our delta G value as 0, because that's the equilibrium point. Delta H would be the negative 300. T would have been still the variable that we would be solving for, and then delta S would have been 1. And so in this case we would have, as I said, 0 is equal to negative 300 minus T times 1. And so now we're looking at 300 is equal to negative T. So in other words, T is equal to negative 300. And so the equilibrium temperature would be negative 300, but we have to remember that that's Kelvin. And Kelvin goes from 0 up to, theoretically, infinity. which means that negative 300 is not a possibility. So there's no temperature where it won't be spontaneous. Alright, so there's no temperature where it won't be spontaneous. That's what we can conclude for this result. So in this case, right, it's going to be spontaneous at all temperatures. Okay? If, let's say for example that T had worked out to be T equal to 30 Kelvin. So 30 Kelvin would represent the temperature when the process is at equilibrium, which means that below 30 Kelvin, either delta G would be negative or positive, and so then you'd have to make an inspection of that situation. You could punch in like 10 for the temperature and figure out what delta G would look like, or you could punch in like 100 for the temperature and figure out what delta G would look like. But in that case then, what you're going to talk about is at high temperatures, the process is, and then you'd either be going with spontaneous in the direction indicated or spontaneous in the opposite direction. So you'd be picking one of those to fill in the blank. And then if you ended up with a situation where delta G is always going to be positive, you would then have a situation where process would always be spontaneous in the opposite direction. So what we're seeing here when we look at this, if we have negative delta H, positive delta S, it's always going to be spontaneous. Alright, so maybe I should put a comma there. And if we have a negative delta H and a negative delta S, now it's going to be a comparison issue, right? And so really the way that this system gets to remain, let me do some erasing here for this piece. So do some erasing. So the way that this system gets to be spontaneous, in other words, have a delta G that is going to be a negative value, is we have to look at this equation. And what we're finding is, with a negative delta H, this term is going to win out, right? So when the delta H is negative, right, a negative value, okay, so maybe I should be writing it like this. So when the delta H is negative, we have a negative term here, but we have a negative term here as well. Well, subtracting a negative is like a positive. So what happens is, in this case, at low temperatures, it'll be spontaneous in the direction shown. Because what happens is, at low temperatures, this term here is not able to overcome this term here, and so the delta G remains negative and therefore spontaneous. So now let's look at the other possibilities. Positive delta H and positive delta S. So now what we're going to find is that with positive and positive, we have a starting point, right, delta H, that is going to be non-spontaneous. But as the temperature starts to increase, what happens is this term starts to outweigh the enthalpy term, right? The entropy piece outweighs the enthalpy piece, and what will happen is the subtraction doesn't change over, and so it starts getting more and more negative, and so at high temperatures, that's what's going to help that term win out. It will be spontaneous in the direction shown. And then the last possibility is a negative delta S with a positive delta H. Now in that case, no matter what we do, because we're going to start with a positive and be subtracting a negative, it's always going to be positive, which means it will never be spontaneous as shown. It will always be spontaneous in the opposite direction. So what we see is when we have opposing delta H and delta S terms, it's going to be spontaneous. The question is in what direction. And so if it's negative delta H, then it's in direction shown. But if it's positive delta H with the opposing delta S, then we're looking at a reverse spontaneity. When it's double negative, it's even telling you low temperature. When it's double positive, it's even telling you high temperature. Kind of use those as indicators. So I hope this didn't bounce around too much for you, but that's basically how you're going to do it. A lot of times the questions will be dealing with what temperature is going to be splitting between spontaneous in the direction shown or spontaneous in the opposite direction, or the other possibility is at what temperature is the situation at equilibrium. But that equilibrium temperature is what creates the dividing line between spontaneous in the direction indicated and spontaneous in the opposite direction. So I hope this helps. Good luck putting it to use for yourselves.